Let us next see change of variables formula 2. So the statement is exactly similar to that of formula 1 with only one difference. Still we have the two functions phi and f. Phi is still continuous and monotonically increasing. Moreover, a is less than b, so that thing is there. The difference is that this time f is not necessarily piecewise constant. Instead, f more generally is a Riemann integrable function. So it includes the piecewise constant case. Conclusion is same. Then the composition of f and phi is Riemann Stieltjes integral with respect to phi, and the Riemann Stieltjes integral equals the ordinary Riemann integral of f. So let us prove this. So in the proof, we are going to first of all note that this composition is a bounded function. Since f is Riemann integrable, it's also bounded. Hence, if composition phi is also bounded, the question is why? Well, if you think about it, say you take an input from this interval, x say, and think of the image of x under f composition phi. What is it? F of phi of x. So after all, it's an f image, right? And since f images form a bounded subset of R, so obviously this special f images also will form a bounded subset of R and will in fact be a subset of the general f images. In the general f images, there you have just f of t, here you have f of phi of x. That is why this function is also bounded. Because it is bounded, we can now ask meaningfully the question whether this is or is not Riemann Stieltjes integrable. If you, in the beginning itself, you do not have a bounded function, then the story stops there itself. Okay. Now let us choose an epsilon. Let epsilon be a positive real number. So what is given to us? That f is Riemann integrable. So let us recall the things that we usually do when, in such a situation. The Riemann integral of f, that is this integral, because it exists, it's simultaneously the upper Riemann integral as well as the lower Riemann integral. Think of it as the lower Riemann integral. So what is the definition of the lower Riemann integral? It's the least upper bound of a set. So because it's the least upper bound, if we make it even smaller, means if we subtract a positive real number, then this number is smaller than the original integral. So it will no longer be an upper bound of that set. And what is that set? That is the set of integrals of piecewise constant functions which minorize f. Since this is no longer an upper bound of that set, so at least one such integral will exceed this number. Okay, so we will get a piecewise constant function which minorizes f and whose integral over this interval will be strictly greater than this. Similarly, thinking of this integral as the upper integral, to that if we add epsilon, because the upper integral is the greatest lower bound of another set, so we will get another set piecewise constant function. I am not going into too details into this thing because we have already done this at least 2 or 3 times. So let me just straight away write the things. Then there exists PC functions f underscore and f bar. You know the notations also. On this interval such that if I write in words, I have to write a lot. F underscore minorizes. Instead, let me write like this: less than or equal to f of x, which is less than or equal to f bar of x. For all x belonging to this, and so these inequalities say that f underscore minorizes f and f bar majorizes f, and minus epsilon. We are not integrating f minus epsilon, okay. From the integral we are subtracting epsilon. The former would be denoted like this. Okay, so this is strictly less than the integral of f underscore, okay, which itself is less than or equal to the integral of f bar, and that is strictly less than f plus epsilon. Okay, so in getting these inequalities, we have simply used the fact that f is Riemann integrable. Now, we can replace these two integrals, the middle integrals, by corresponding Riemann-Stieltjes integral by using the previous lemma. Previous lemma means change of variables formula 1. Why? The reason is that they are piecewise constant, which the original f may not be. And previous lemma means I never seem to be able to remember these numbers. 11, 10, 5. Yes. By lemma 11, 10, 5. Minus epsilon is less than. Now in place of this we will write, now the interval will also change. F underscore composition phi d phi. Okay, so this is ordinary Riemann integral of this PC function. This is the corresponding Riemann Stieltjes integral if you consider the function phi. Similarly, we have this one, because this is also piecewise constant and that is less than that. All right. Now you see, this is a simple thing to verify. I am not going to show in detail how this is true. The author has also simply mentioned this. The thing is that since f underscore composition phi and f bar composition phi are PC, these are piecewise constant functions, and phi of t is less than or equal to f composition phi of t, which is less than or equal to f bar composition phi of t for all t belonging to a comma b. Not only are these piecewise constant functions, but the first one minorizes f composition phi and the second one majorizes f composition phi. So because of these things, what can we now say? We can say this: the integral of f underscore composition phi d phi, integral means Riemann Stieltjes integral, is less than or equal to the lower Riemann Stieltjes integral of f composition phi with respect to phi, which is less than or equal to the upper Riemann Stieltjes integral d phi, which in turn is less than or equal to the Riemann Stieltjes integral of f bar composition phi d phi. Why? Well, you see, you keep in mind that in the beginning itself we said that f composition phi is bounded. Alright, and for bounded functions, just like ordinary Riemann integral, lower Riemann Stieltjes integral is less than or equal to upper Riemann Stieltjes integral, that we already know from theory. What else? How are we getting this inequality and this inequality? Well, you see, what is this lower Riemann Stieltjes integral? That by definition is the least upper bound of what? Of the set of integrals of piecewise constant functions that minorize the original function. This is one such function. It is piecewise constant and it minorizes this function. So because it is such a function, so this leftmost integral is an element of that set, whose least upper bound is this lower integral. So obviously it will be less than or equal to this least upper bound because it's an upper bound. Similarly, the element of which this rightmost integral is the set of which this rightmost integral is an element of that set this upper integral is the greatest lower bound. So because it's a lower bound, it's less than or equal to that. Okay. Now you see these inequalities and you see these inequalities. What do you see? Already these terms, this term and this term are the boundary terms of this chain of inequalities. And then if you look at the middle terms, this term and this term, you have got another term to the right of this, which is this, and another term to the left of this one, which is this. So you can now replace these middle terms by these even more middle terms, which are more inside this chain of inequalities, and that is why here itself I can modify. Hence, so what shall we do? We just replace this by ordinary f composition phi and lower Riemann stages integral we write, that means this one. Here we write f composition phi and upper Riemann stages integral. Okay. So then what are we getting from this final chain of inequalities? See, first of all, 0 is less than or equal to this minus the lower Riemann stages integral. Because we know that for bounded functions, upper integral is greater than or equal to lower integral, both Riemann as well as Riemann stages. However, this upper integral itself is less than this, right? And the lower integral, forget that minus for a moment, okay, only the lower integral, that is this one, is greater than this. So minus of this will be less than, the inequality will get reversed, less than this. So minus of this is less than minus of this. That means and what is this? This is 2 epsilon. So the difference between the upper and lower Riemann stages integral, while being non-negative, is at the same time less than 2 epsilon, but epsilon is arbitrary. So the only possibility for that difference is to be 0. It can only be 0. If it becomes positive, then you can choose an epsilon which is sufficiently small to create a problem here. Since epsilon is arbitrary, we must have minus thus if proposition phi is Riemann still is integrable. And not just that, if you now go back to those inequalities, okay, the inequalities that we have before these, you see that the integral has to be equal to this Riemann integral of f. Okay, so that concludes the proof. And with the help of this proposition and the previous lemma, we finally have our change of variables formula 3, which is the result we have used always when making substitutions in integral in school calculus. And let's see the statement. This is the last result of this section, and also the last result of analysis 1. Change of variables formula 3. Let a and b be real numbers such that, let me write st, a is less than b. And the phi that we will now choose, it has to be chosen differentiable as well, besides being monotonically increasing. Let phi be a differentiable monotonically increasing function such that its derivative is, oh, and what the hell, I did not write what phi is. Let me write it there. Okay, sorry about this. I forgot to write what phi is. Okay, so all these things is Riemann integrable. I remembered I didn't write something when I thought of the domain of phi prime. It is this. Additionally, let f from this be Riemann integrable. It's fading already. Let me just put a little ink. I need a little. Oh, I have run out of ink also. Yeah, it's there is one more line. I have to write like this only. It is Riemann integrable, then this function f composition phi times phi prime. Okay, so this part is composition and this part is multiplication. From a comma b to r is also Riemann integrable. And the Riemann integral of f composition phi times phi prime is equal to the Riemann integral. Let me write here itself of f. So you see that in this final conclusion, I mean in this final result and its conclusion, there is no Riemann-Stieltjes integral. You may have been thinking where all these things are going, because we were going on and on with Riemann-Stieltjes integral, which however is not there in school calculus. But you can see that now we have reached this result, that Riemann-Stieltjes integral was a tool, a means for us to reach this result. So how is it a substitution formula? Well, that's easy. If you change the notation slightly, we are not writing things like, dx, we are not following in Terence-Tau's notation. But if you follow, this equation is going to look like this. F composition phi means f of phi of t phi prime of t, or if I go really back to whatever we wrote in school, d phi dt is equal to So what you really did is this. So you made the substitution x equal to phi of t. So then what do you have to do to dx? Then dx will be d phi dt times dt, right? So in place of dx you wrote d phi dt times dt, in place of x you have written phi of t, and the original limits of integration, the lower limit is phi of a and the upper limit is phi of b. So they turn into this, a and b. Okay. Yes. If you think this part may look initially a little confusing to you, how is phi of a becoming a? Well, you see the substitution. What is the lower limit? The lower limit is phi of a in the x variable. Right, and the upper limit is phi of b, again in the x variable. But we are replacing that with the new variable t. T is the new variable. So t should go from A to B, because then only x is going from phi of A to phi of B. That's how I think you remember whatever you did in school calculus while making substitution in integration, and now we have actually shown why this is true. Oh, and one more thing, what about the proof of this last result? Well, that follows actually directly from the lemma and proposition. You don't have to do anything. You just go back, you write down the two statements together, looking at them simultaneously, you will immediately see that yes, this should be true. And that's it. That's it means we have completed analysis 1. The exercises are still there, which we will do maybe in 1 or 2 more videos. And then analysis 1 is complete, it's over. And then we will start analysis 2. Now I am thinking of something which I think I said in the last video also, or I mean yesterday's video. The thing is that I want to transfer this differential equation. I don't want to keep it with topology. So on Mondays from now on, I mean after completing this thing entirely, after that we are going to do analysis and differential equations on Mondays alternately, and the day where we do topology, we will do only topology. Okay, so that will be all for today, and tomorrow we have number theory, I think. Yeah, so see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.